我是随时可以开始。
可以开始，您可以开始。
Okay. Right. So, first of all, thanks so much for inviting me to give a talk about my recent research on prompt learning. It's a very exciting area that just started maybe a couple of years ago. So in this talk, I'll mainly discuss from a new perspective how prompting can be used as an can be seen as a new API to achieve interactive visual intelligence. Right. So let's start by talking about how we can um, do visual intelligence, right? We can train a big neural network using a lot of training data, and we can achieve amazing performance on a number of different computer vision applications like image classification or object detection, right? It's very powerful. And if from when it comes to deployment, we want to deploy the model for the end user. What is important for the end user is the API, right? What they care about is how they can interact with the machines, with the AIs that we develop for achieving their goals, such as object recognition, image classification, right? And in terms of APIs, the conventional APIs that end user often use are twofold. The first is object of interest, which means that typically the end user defines what they want to classify, right? The object of interest like dogs, cats, or birds. That's what they want to classify in their downstream applications. And the second API that is commonly used is the input during test time, right? So we have the model that is already deployed in the application. And then the user gives each time a test input to the model, and then the model will produce the output based on what the model is defined during training, right? For animal classification, for office object classification. So these are the two APIs that are often used by the end user, right? And typically, it's worth noting that the model is often fixed, which means it is only programmed to solve one task, a specific task, like animal classification, which means the model's behavior is fixed during training. And let's look at more a specific example of what this means, right? So say we have this CIFAR 10 data sets. We want to train a model to do 10 classification, where we collect images for these 10 classes: airplane, automobile, bird, cat, deer, and so on and so forth. Then we train this neural network to produce a probability distribution over these 10 classes. And this model is fixed, right? Because it's once the training is done, the model weights cannot be changed without another round of training, right? So at test time, the model can only perform the classification task on these 10 specific classes, right? Airplane, bird, cat, and so on. If we want the model to recognize new classes that are not seen during training, it's impossible because the model has a fixed architecture, right? You have a backbone and you have a linear classifier that can only perform this 10 classification, right? So in this case, the model wouldn't be able to classify the tiger classes, right? If the user wants to add a new class, say tiger, then the model will fail completely. But what if a better way is we have the end user to ask the model like what to distinguish between a photo of a cat and a photo of tiger. And these are the prompts to be given to the neural network that was pre-trained on large data sets. And in this scenario, we have this neural network that can recognize that can do a classification on these two classes, right, cat and tiger, and then produce a two-class probability distribution to indicate how likely this image contains a tiger or a cat, right? So we would like to have this new way of interaction with the machine, with the AI, and this is called prompting, which is a very new paradigm for achieving artificial intelligence, right? We have this, and these concepts originated from the natural language processing community, and the most popular one known by the public general public would be ChatGPT, right? You can interact with the ChatGPT model by giving it a prompt, basically a sentence. Then the model return you an answer to adjust the specific question that you give to the model, and you can interact with the model in a conversational way in using prompting, right? And prompting has also been widely studied in computer vision in the last couple of years. We have seen this clip model, right? It's very popular. I believe many of you might have been using this for your own applications, right? You have these two encoders. That one is used for projecting text onto an embedding space. You can give the model a specific prompt, like a photo of a plane, a photo of a car. Then the model can perform open vocabulary image classification on whatever categories you give to the model. And we have also seen this open vocabulary object detector that we developed in the 2022 published on ECCV. So this is an open vocabulary object detector that can take as input a text prompt or an image prompt that specify the object of interest that we would like the model to classify. Right, so we have a cat. We have seen this model can classify cat and bird based on the input, and we also have seen this very famous model called segment anything that is developed by Meta AI. So instead of using text prompts, this model is based on visual prompts where you can basically modify the input by giving the model either a point or bounding box or even some region or and also the text to specify which region or which class you like the model to produce segmentation masks in the images, right? So it's quite different from the previous paradigms. And we have also seen how prompting has been used in text to image generation. You basically have, let's say, the DALL-E 2 model, right? Or maybe the stable diffusion. You give the model a human written text like a teddy bear painting a portrait or a photo of an astronaut riding a horse, and the model can produce realistic images with very high quality. And finally, we have this application of visual dialogue that is also based on prompting. You can have this large neural network, and you interact with the neural network by um, basically asking questions, and the model will return you some answers, right? Specific answers. You can also ask the model to explain why a specific image is funny, and this is achieved by the very powerful GPT-4. So all these examples are prompting use cases in computer vision. So and what is important for the prompting model is the prompt that you give to the model, that you provide to the model, because a good prompt is essential for achieving excellent downstream performance, right? If you have a bad prompt, then the model wouldn't be able to steer it to behave in a specific way, right? So the first study that I would like to introduce is this learning to prompt for vision language models. So we focus on this specific model that is CLIP, where you have two encoders, right? You have an image encoder, you have a text encoder. And these two encoders are trained using contrastive learning. Basically, the main idea is to align the text with the corresponding images in the joint embedding space in such a way that after training, the model can produce a similarity score for a pair of image and text, right? If the text describes the image, then the similarity score will be high, right? Otherwise, the similarity score will be very low. And after training, what is amazing is that this model can allow users to do prompting to perform open vocabulary object recognition. Basically, you give the prompt to the text encoder, like a photo of a plane, a photo of a car. Then the text encoder will produce for each prompt a specific classification weight vector. Then you can basically synthesize any weight vectors for any category to do image recognition. But now the problem is, how can you engineer a good prompt, right? You can try a variety of different prompts, right? And these are the prompts that are designed by the OpenAI team, which developed the CLIP model, right? You can see the variety in the wording, right? A photo of something, a photo of many something, right? It's very difficult to engineer these prompts. And the worst case is that if you try to change to modify a little bit in the prompt, you can see drastic changes in the downstream performance. For instance, on this Caltech 101 dataset for object recognition, you use a photo of class, right? You get 80% accuracy. And if you change, just add a specific word before the class token, you can improve the performance significantly by over maybe around 6%, right? This is a very significant improvement by just changing the word very slightly. So basically, a slight change in wording could give you very different performance. So in this case, to address the downstream adaptation problem, we borrow some idea from the natural language processing community and develop this simple technique called context optimization, where we only optimize the context tokens while freezing the class tokens for these input prompts, right? And we can basically learn these prompts by backpropagating the gradients from the cross entropy loss, right? It's a very simple way of optimizing these context tokens, and by using context optimization, by only learning a few tokens, input text tokens, we can achieve significant improvements in the scenario of future learning, right? We have, you can see the varied on the x-axis, right? We have 1 shot, 2 shot, all the way to 16 shots. And what we observe is the performance of context optimization outperforms the 0-shot clip baseline, right? Which is shown as the purple star asterisk. And this is very exciting because it shows how you can address future learning by adapting large vision language models. And not only future learning, we also have shown that prompt learning is very effective in the domain generalization scenario, where you learn the prompt from one domain, such as ImageNet, and then you apply the prompt to different scenarios, like under different distribution shapes, maybe sketch images, or maybe images of different image styles. You can still obtain some decent improvement. And in terms of interpretability, I would say the prompt learned from data isn't very interpretable. So we have some observations. The first is a few context tokens are somewhat relevant to the data sets you are working with, such as Fluffy and Paul, that describe the characteristics of the pets images, right? But if we try to connect all the prompt tokens into a sentence, then it doesn't make much sense, which means we need to balance between interpretability and performance when using prompt learning in real world scenarios, right? And the second study that is a follow-up of the previous one is conditional prompt learning for vision language models. So in this study, we take a step further to study how context optimization can generalize to new concepts of the same data sets, right? So here we train the prompt on some base classes for scene recognition, right? So you can see these example images, arrival gate and cathedral, right? We train these prompts, a single prompt for different classes, right? You can get 80% accuracy. And if we apply the same prompt learned from those base classes to new classes, but still of the same data sets, like wind farm or train railway, you can see the performance drops significantly from 80% to 65%. So the conclusion is the prompt actually only works for a subset of classes, which means the overfitting problem, right? And this isn't what we want for the prompt, because we expect the prompt to be generalizable to capture the nature of scene classification, right? And so here we can see more further classes of this prompt of applying the prompt learned from some base classes to unseen classes within the same data sets. We have flowers 102 dataset where the performance drops by 37%. We have action recognition on UCF 101. We have over 25% of performance drops. So now let's discuss what is a good prompt. So we argue that a good prompt should contain instance-specific context. So for instance, in this cat image, if you have this prompt a cat, it might be distant away from this image. But if we just add some specific keywords to this image, like a lazy cat or lying on the ground to the cat, we can actually push the text features closer to the image features in the embedding space. So in this way, we can steer the model to produce more meaningful text features, right? More specific text features to this specific image. And this inspires this architecture, conditional context optimization, where we have this MetaNet architecture, which takes as input the image features and produces a single token that is combined with different context tokens to be given to the text encoder to produce text features, right? So in this way, we can produce context tokens that are specific to the input image, right, to solve the generalization problem. So our experiments show that conditional prompt learning is much more generalizable compared with the standard prompt learning on the S1E11 data set. We have over 15%. We have over 10% performance improvements on a number of different data sets. UCF 101, DTT for textual recognition, Stanford cars, flowers, 102 for fine-grained visual recognition. And when it comes to weakness, actually conditional prompt learning is very slow in terms of training because the text input is essentially a 3D prompt tensor and is generated for each specific input. So you need to reduce the batch size to 1 in order to fit the training. So if you want faster training, that I would recommend using multimodal prompt learning, right? You have a text prompt, you also have a visual prompt that adds some learnable parameters to the visual input space. And basically we can learn the transform architecture to bridge the gap between these two modalities, right? And we can obtain some improvements while reducing the training time significantly. And if you have more compute resources, I would recommend using neural prompt search. That is where the main idea is to add some learnable modules to the transformer architecture, to the internal model. Then you basically use some existing differentiable neural architecture search algorithm to identify the optimal configuration of the model. And you can obtain some improvements compared with using individual prompt modules such as adapter or LoRa. Right. So yeah, we have talked about where you have access to the model weights, right? You apply prompt, then you learn the prompts by backpropagating gradients through the model. But in the case but not always the model weights are accessible to the user, right? So it's sometimes it's possible that some models are only provided as APIs, right? Such as ChatGPT or maybe the DALL-E image generation model, right? It's very common that those big companies able to produce large foundation models only provide APIs to the end user. So in this case, we would not be able to apply prompt learning to improve the downstream performance, right? And there are various reasons why this model as a service is becoming increasingly popular, right? Because of the model size of the of foundation models is very large, right? It's enormous, which means not every user has the compute power to run those models. And by using APIs, we can also improve accessibility, right? More users with different backgrounds can use the model. We can also improve maintenance because, right, if you have internal model maintained by the companies behind. They can improve model, but still use the same API for the end user, and there are different reasons, so on and so forth, for using APIs instead of model weights in the deployment scenario. So in this study, I would like to introduce visual in context learning. So this is a new concept that has recently been started in the computer vision domain. So what visual in context learning offers is that users can actually customize models by only tuning in context examples. So before introducing how we can achieve in context learning, let me give you some examples of how in context learning can be applied in practical scenarios. So in this case, we want the model to produce edges, right, to do edge detection. So basically, what we provide, give to the model is just some in-context examples containing an image and the edge maps, and these serve as the kind of the training data for the model, right? And the model can produce for the test input the edge map. But if we change the input, right, we give the input different forms of input, like we want the model to colorize the input, then we can basically change the input from a pair of black and white images, and also its colorized version. Then we give the model a test input. Then the model will produce the corresponding colorized version for the model. We can also achieve different objectives by giving the model different types of input with different patterns, right? And this is in context learning. It's a very new concept in the field of computer vision. So now let's talk about how we can train a model to achieve in context learning. The training is pretty simple. You basically use masked image modeling. You train a model to fill missing patches in images using some specialized data sets, such as these computer vision figures which are basically grid-like images collected from computer vision papers. And after training, the model can perform in-context learning, right? Basically, you give the model a pair of examples. So in this case, we want the model to produce segmentation mask. Then in this case, you give the model an RGB image with the segmentation mask. Then basically you give the model another test image to construct this in-context input. Then the model will automatically complete the missing part by producing the corresponding segmentation mask by following the pattern it found on the in-context examples, right? And in our recent research, we found that the choice of in-context examples matters a lot, right? So given this foreground segmentation example, what we did was to randomize the in-context examples, give the model different examples, and what we observe is that the variance of the performance is very large, right? So it can range from 20% lower than 20% accuracy to as high as 80% accuracy. And if we take a closer look to zoom into the prompt, what we can see is that the best prompt that gives you the best performance looks more similar to the query image, right? But if we look on the very right-hand side, the worst prompts, which we can see that a prompt is very dissimilar to the query image, because the prompt is basically a black and white image, but the query prompt is an RGB, right? So we can have we can find some patterns in this prompt. So in order to solve this problem, we propose this we use the idea of prompt retrieval and propose a general framework to solve this problem, where the main idea is that so the model is only given as an API, as we have mentioned before, right? And so in this case, we have a database, we have a query image. Then we basically, the main objective is to learn a score function that can give you a high score for the image that fits the in-context example, right? So in this case, we use the API's output as a supervision signal, right? So we have two solutions. Basically, the first solution is unsupervised prompt retrieval. So we have a candidate. So we train this. We basically use off-the-shelf model to extract features for each input image, right? And then we basically for each query image, we find the candidate that gives you the most similar features, right? So we assume that the off-the-shelf model can already extract features that contain semantics. So basically measure the semantics between the candidates, each candidate in the source data set and the query image. And we select the candidates with the most similar features to be used to construct the in-context inputs, right? And the second method is a supervised prompt retrieval method, where the main idea is that we want to directly optimize the in-context learning performance. So given a database, right, we use each, basically we loop into each training image, right, as a query image. Then we use the remaining images as the source data set to construct the in-context learning inputs, right? And then we use the API to produce for each in-context example a performance value, right? And we rank the values from high to low, and then we collect the top 5 positive examples to group them, and then use constructive learning to separate between the top 5 positive examples and the top 5 negative examples. So basically train another neural network that can give you this score function. And in terms of the performance, we compare prompt retrieval with random selection, right? So here we select 3 tasks. Like the first is foreground segmentation, the second is single object detection, and the third is colorization. And from the results, we can see that prompt retrieval, whether unsupervised or supervised, they all outperform the random selection method, which basically randomly select the in-context examples for a specific query, but within the same class, right? And in terms of the number of in-context examples, we found more in-context examples is clearly better, right? It seems like we can view this in-context example as some sort of training data. If we give the model more training data, then the model basically has a more comprehensive view of the data distribution, right? So we can understand the patterns encoded in the in-context examples and produce the desired results for the end user. So does the order of in-context examples matter? Where our experiments show that the order doesn't matter too much, right? So basically try different orders for these different methods. And what we found is the variances of different orders are actually very small, right? Less than 0.5%. So we can conclude that you can basically, from the end user point of view, they can randomize the order of the in-context examples, but increase the number of in-context examples in order to achieve a better performance. And finally, what we would like to understand what are good in-context examples to use from these prompt retrieval methods. So basically, what we found is the closer the in-context example to the query image, the better the performance. And this is very clear if we compare the in-context examples chosen by the unsupervised prompt retrieval method and the supervised prompt retrieval method, right? So if we look at the first example, we can see the query image, the in-context example chosen by the supervised methods is closer to the query because the two kits have a similar viewpoints and pose, right? But the example chosen by the unsupervised method only captures the semantics, that is the keys, rather than other more specific attributes such as background, pose, and appearance viewpoints. So the conclusion is clear. Supervised method is better than the unsupervised method. So now we can conclude this this talk by giving some takeaway messages. So the first is, well, if you can use prompting, if you can have a prompting architecture, then use prompting because it's more flexible. It provides the user with versatile functions, right? And the prompting architecture might be more generalizable, as we have seen from the previous research, and more importantly, gives a more better human user experience because it has prompting is more interactive in a sense that we can basically give the allow the users to give interact with the machines in a very natural way using natural language, right? And if you can learn the prompts rather than handcrafting prompts. And in order to achieve better generalization, you may want to use conditional prompt learning, right? But it's compute intensive. So you need to trade off between performance and compute. And finally, if you are unable to have access to the model weights, right? It's basically the black box prompt learning scenarios, and then you want to use prompt retrieval rather than handpicking in context examples. So yes, that's the end of this talk. Thanks very much for your attention. So yeah.
OK，感谢凯阳老师啊，
嗯
我们这块儿应该就可以，对，我们就可以那个大家想提什么问题就随时提就可以，然后或者说如果
可以可以。
好意思这个开音频提问的话，可以发到这个 chat 里啊，我们可以看一下。对，要不先一般情况下，万里老师都不先问几个问题，万里老师是不是忙去了？没有的
哎
话，哎
哎，
啊，万里，
凯阳，哎，你做
嗨嗨。
这个挺有意思的，而且说你们在这个 prompt 做的比较早嘛，后头大家都发现这个方向还挺好的，很多人都在 follow。对，而且就说用 prompt 的一个好处是说很多时候你的这个 backbone 不见得要来 fine tune 嘛。对，有
嗯嗯。
几个就是你有一页的那个，就说其实是你们那个忘记是 IGCV 还是 PAMI 的那个工作里头，就说你这个里头也讲了，就是那个就是说你会用 visual 的这个learnable 的这个 context 作为 visual 嘛？你好像有一页是，就说一个是可以去修改一些文字，发现其实效果会更好。嗯，
是的，是的，应该是正常的
对，
修改的这
18页可能是，
这一页是吗？
对，就
啊。
说首先是修改文字会得到比较好的结果，这个本身都是比较有意思的事儿。那另外的话，你这个 V 其实是并不是某一个 word，而是就说是 prompt tuning 一般的那种 continuous 的这些值了，是吧？
对对对，它是一些连续的一些向量，所以
嗯。
他们其实很难去了解它本身到底学到了什么具体的意义吧。
了解，那这个就是实际上是很多现在在做的 visual prompt tuning 的这种类型的方式，而你们开展的比较早，了解了。另外的话就说，其实现在要做要做好这件，就说要做好这个 tuning 的这个事儿，一种是可以 prompt 的嘛，一种是说也有一些就像那个 LoRa 这种类型的啊，就说或者是说 ladder 的这种类型的。就是去在中间增加少量的这样一些可 learnable 的参数和 learnable 的这些 feature。目前的话，在你 overall 的看来，在这方向上的哪一种才是更有效的？是纯的只加 prompt 好，还是说利用其他的方式会更好？目前你的看法以及未来你觉得在这方面，如果我们有了一个 pre-trained 的这样一个 large model 或者是 foundation model，具体应该怎么做？
这个挺很好的一个问题，就是确实在我们之前的实验中发现说，如果其实可以分成两个场景，一个场景就是你有足够的训练数据，那你有足够的训练数据的情况下的话，一定是训练更多参数的一个方法会更好，比如说 LoRa 或者是 adapter 或者是 把它们的结合，就是我们之前也有做过像 neural prompt search 这样子的工作，去寻找说如何结合不同的这些模块，使得下游的 performance 会更好。那这个是在你有足够的数据量的情况下，是越多参数越好，会更加拟合你这个下游的任务。那在
嗯
没有参数量，在没有足够训练数据的情况下的话，prompt learning 的效果会更好，而且优势也非常明显。在few short learning 或者是在一些有嗯数据分布的一个偏移的情况下，prompt learning 都会给下游的 performance 会带来更好的一个效果。所以其实还是比较看你下游任务的呃一个数据量的情况。对，那如果是未来的一个趋势的话，呃，我会觉得大部分的可能比较好的场景还是在那种black box 的一个也就是用户只能拿到模型 API 的这种场景下，就是也比较现实，因为模型的巨大，使得模型很难在比如说手机或一些移动的设备端去运行，所以一般会在云端去做这么一个应用。那这种情况下，可能用户拿到了就不一定是只是一个 API 的形式。那在这种情况下，如何让一些下游的公司呃去提高这个在下游任务的这个 performance 的话，可能在 black box prompt learning 这个场景会更加的有用。所以我觉得，但这个场景好像现在并没有很多的research 去关注到，所以这个其实是可以去探索的一个场景，然后也是可以跟 in context learning 结合，也就是如何在你的模型的 input 去改变，去做一些微小的改变，或者是一些提供一些几个若干个的这么一个例子，让模型去改变它的行为方式，去产生不同的功能。我觉得这个还是比较有趣的一个去探索的方向。
好的，谢谢。
嗯
哦，好，那万里老师问完了，我问一些问题吧，就一个是说，因为我们现在也在做一些这个多模态的大语言模型，然后凯阳老师您应该还没有就实际做过这个事情，但是我看那个紫薇老师他们做了一个就 alter 那个工作，然后我们其实现在发现一个事情啊，其实跟您现在讲的这个事情很比较相关啊，就是这个visual 的这种 in context learning 啊。实际上，在多模态大语言模型这个背景下，我们现在看起来，就除了紫薇老师那个 alter 那个工作，他们对于这个 in context learning 专门有些设计啊，他们的那个多模态的大语言模型，在有 in context learning 的 sample 的情况下会表现更好。其他情况，现在的这些多模态大语言模型都没有，就是说加了 in context learning sample 都没有变得更好。这一点就虽然您没做过，但是因为您那个之前这个 Clip 这个时代做很多这样的工作嘛。就想问问您的看法。就我理解，是不是说大家应该在这方面还是要有一些底带？嗯，
嗯，我不太理解你说这个不同的，你再描述一下。
对，就是多模态的大语言模型，就是现在就
嗯
很多做法是说，大语言模型作为基座，然后它会接一个 visual encoder 嘛，然后比如说 Clip Pretrain 的 VIT 作为一个 visual encoder，然后转换成了 feature 之后，再把 feature 转换成 token 给到大语言模型，这是一种现在很多人都在这么做的一种做法。然后这种模型现在就是很自然的会想到的就是我们是不是可以给多模态的 in-context learning sample，就因为原本大语言模型 in-context learning 很 work 嘛，这个area analysis，但是本身我们如果加了这种多模态的，比如说 C 牌这个数据集，训练的时候他们没有见过，但是我这个评测的时候，我想我给一些 C 牌的，比如说我给5个例子，然后这5个例子作为 in-context learning sample 给到它之后，其实大多数的现在的 SOTA 的这些多模态的大语言模型，大家并没有表现得更好。就比如说会陷入到什么情况？比如说有情况就是，我给他了一个这个汽车的这个图片作为 in-context learning sample 之后，它可能这个模型就坏掉了，它就会倾向于回答你所有的类别都是倾向于这个汽车这个类别，就可能会有这种情况发生。就我理解这个，一方面是说现在大家的多模态的大模型的能力本来就没有那么好啊，就肯定是没有做到这个能力特别好的这个情况。然后另外是不是说本身这里边也应该有一些 architecture 或者是训练的逻辑上的 design？嗯
嗯，对，因为 对，确实在语言模型足够大的情况下，它能够去产生这种 in context learning 的一个行为，但是确实在视觉领域吧，或者说视觉跟语言结合的领域，还没有比较突出的一个工作去展示说 in context learning 在视觉领域具体会体现出什么样的一个特性吧。对，然后针对你刚才说的这个问题，就是说在基于语言模型的基础上，我们去加一些多模态的 input 啊，或者是加一些能够处理视觉信号的这么一个模型的情况下，它可能 in context learning 不太好，所以这种情况下，我觉得如果是我会去探索的，就是怎么在训练方式上直接去引用 in context learning 去训练，就是你可能可以在训练的时候，就是让这个模型的输入去接收有 in context example 这种类型，就一个 input 一个 output，或者是几对的这么一种 input output，直接让模型在训练的时候去接收这种 in context 的一种信号，那它的可能在 testing 的时候，可能泛化性会更好。那如这种方式的话，我之前有见过一些语言模型的话，在这方面的 paper，就是你可以用meta learning 吧，meta learning 去做这种学习
嗯
训练啊，你在 input 的时候做一些加一些 in context 的 input output，那你测试的时候也是用 input output，然后去一个是 meta training，一个是meta testing，这么去连接起来。那可能你可以尝试一下用从 meta learning 的角度去解决这个问题，也许能够有一个不错的效果。至少在language 模型的领域，我见过这么类似的文章。
嗯，OK OK，了解了。对，就这块儿感觉还是应该多模态的模型有挺多可以做的。就现在大家这块儿并没有一个明确的结论，或者说没有特别好的表现嘛。
对对对对对，然后我个人是很喜欢 in context learning 这么一个概念，因为确实在视觉领域很少去见到类似的一些文章吧。对，
嗯。然后，但是您
嗯，
您之前刚最开始就我理解，您的工作应该也是就是第一批吧，去提visual 的 prompt learning 以及 visual 的 in context learning 的这种概念，但是您当时提这个概念的 motivation 是不是也是觉得本身大语言模型 NLP 这边他们大语言模型有这种能力，所以视觉 somehow 我们是不是也可以让视觉模型或者说多模态的模型能有这种能力？对方我想知道就
是的，
是您当时
是的，确实是这么 motivation 也是从自然语言处理那个领域来的，因为这几年确实主要的一些进步啊，一些突破都是在视觉语言都是在语言模型那个领域嘛，像 GPT 啊，后来的啊、BERT 啊，像后来 GPT3啊这种出现 in context learning 的行为方式之后嘛，还有后来的 train of thought prompting，所以我们也之前一直在关注说语言模型它这个领域的一个发展趋势。那当时就看到prompting 啊这种 in context learning 的这么一些比较新颖的概念，所以我们当时就会思考怎么去怎么在视觉这个领域去用到这个概念，因为这个概念不仅在于它新颖，对吧？但是它也提供了很好的一些呃，特别是针对下游任务的一些功能吧，对。因为 in context learning 它能够使得模型在你不改变模型的情况下，你只改变它的模型的输入，对吧？在模型输入上给定不同的一些结果或者不同的一些example input output 的这种 example，那模型就能产生出特定的一些输出。那这种的话，这种可以说这个范式吧，还是比较新颖的，而且是值得去探索的。
嗯。那您本身那个后边的一些规划会再继续做一些什么工作，或者您觉得就是这一块儿的方向上，对大家来说有什么建议啊？就是
其
this
实
work，
后续的话如果因为我去做的话，我肯定还是会去关注说，在视觉语言模型上吧，对。但是嗯，对，因为很难就是 如果只关注视觉领域的话，其实现在很难，可能会有一个比较大的一个突破吧。而且现在在语言模型这么强大的一个情况下的话，我觉得结合视觉跟语言模型的话，也是一个比较呃值得去做或者是比较 make sense 的方向吧。你可以结合视觉语言模型去做一些不只是或者说 specialist 的一些模型，而是一些 general purpose 的模型，或者做一些能够产生出一些多功能性的一些模型，对吧？一些呃或者一些 visual assistant，能够你在给模型 prompt 不同的 input 的时候，模型能够产生不同的呃 behavior，不同的功能性。那这个其实也是目前这个领域并没有去很多探索的地方吧，就是去做一些 general purpose 的模型。对啊，
嗯
然后对，然后个人的话对embodied AI 也是很感兴趣。那 embodied AI 因为我们视觉语言模型走到最后，你当然要结合多模态，才是更加符合人工智能的一个发展趋势的一个愿景吧，对吧？你要接受不同，去处理不同的一些啊、模态的信号，input 的信号。那现在目前来看做的比较好的，我们就是视觉跟语言。那之后可能还会加上一些其他的sensor，其他一些传感信号，比如说一些声音呢，比如说一些触觉，还有甚至是 action，也就是最后肯定是会过渡到这个具体的一个表现方式。那最后可能就是用机器人的一个形式，embodied AI 的一个形式去发展。所以我觉得 embodied AI 也是一个值得探索的一个方向吧。对。
嗯，了解了了解，就看看大家有没有什么问题，就也不是说就只有我和万里老师可以提问，大家都可以提问。就是凯阳老师
呃，
是
凯
其中你说，
凯阳老师你好。好。对，我刚刚
嗯。
在想啊，就是我在想 NLP 为什么 in context learning 如此的 powerful，是因为它的 pre-training 阶段它的训练语料已经很丰富了。然后我在想微视领域，in context learning 我们可能期望做到的一个效果就是，比如说在自动驾驶场景里面，我看到一个水洼或者看到一些 corner case，我可以通过 in context learning 能够很好解决。但是解决这一点的话，我想可能还得回到 pre-training 那一段，因为如果模型它没有见到这些 corner case 图片，我们在推理阶段给它这些 corner case，它会推断的很好吗？就是想问一下老师对这个的一个看法。
嗯，对，其实这方面的话，如果我们去说，语言模型它数据量足够大的情况下，会产生一些哪些新颖的行为方式？比如说 in context learning，呃，其实大家也会 argue 说，你其实在预训练的阶段已经见过了很多的数据量，特别是特别是文本数据嘛，所以很难呃去有一个定论说一定是这个数据一定是之前没见过或者是怎么样的一个情况，因为特别是现在大的语言模型 training data 都是没有公开的嘛。那回到这个视觉的问题来看的话，嗯，我觉得如果要去在自动驾驶的场景下，或者是其他的一些视觉的应用场景下的话，in context learning，我觉得要解决这个问题，可能还是得从首先从 architecture 的角度，就是如何让这个模型能够啊、去处理这种 in context 的 input。因为目前的话，其实比较通用的话，还是像Flamingo 那种方式，对吧？就 Flamingo 是呃，应该是 DeepMind 他们开发的一个视觉语言模型，其实就是把语言模型，然后加上一些能够处理视觉信号的一个模型去做 in context learning。但是在视觉领域的话，其实啊、特别是自动驾驶领域，我们可能还要涉及到分割，涉及到是一些点云的处理，所以其实 architecture 的呃的一个开发的话，其实也是一个呃比较应该去探讨如何能够开发出能够比较适用于 in context learning 的这么一种 architecture，对吧？所以我觉得 architecture 的话也应该是去探讨的一个方向吧。然后呃，对自动驾驶领域确实，我觉得 这方面可以去探索，对。但是我之前并没有太过多的关注自动驾驶这个领域。
OK，好的，那个对，还看大家有没有什么问题。凯阳老师是就最开始在做这个 Visual Prompt Learning 和 Context Learning 的一批人，所以机会也比较难得。大家要是有问题的话，可以现场交流。没有的话，我再问一个吧。我刚才没有问完，我想看大家有什么问题。就是说，就还是那个刚才万丽老师也问到这个，就是本身现在 prompt learning 包括那个多模态的这种，然后也包括本身就是 LP 的这种，它学出来的这个东西，这个 prompt 它自然是更好的，但它就是一些这个 token，然后这些 token 实际上是并没有实际意义的嘛。然后就针对这一点，其实我有一点 confused，就是我也拿不准。就是说，比如说我们去评价一个模型，不管它是多模态的模型还是大语言模型的这个能力的时候，我用上 prompt learning 这种方法得到的这些 token，然后我去 inference，它肯定是结果更好的。但是这个到底是本身我 prompt learning 的方法带来的能力，还是说它模型本身就是有这个能力？我 prompt learning 其实只是激发了，或者说更好的去比较了大家各个不同的这种多模态大模型的能力。就这个事情，想听听凯阳老师的想法。
嗯，我感觉这一点就涉及到了，就是它prompt learning 或者是这个模型的可解释性吧。但是
嗯
其实这个是一个真的很难的一个问题，现在 AI 啊，或者是CV 啊，甚至是 NLP 这个领域也是没有一个能够下定论的这么啊、一个问题嘛，所以其实很难去解释说能够它到底是他学到了一些比较有意义的一些词呢，还是说只是说增加这个参数量能够带来的一些效果？但是就是从我们的实验中去做不同的对比的话，比如说对比 prompt learning 跟对比你直接在一个模型的比如说 output 去接一个线性的一个分类器，或者是在模型里面加一些可学习的参数的情况下，那 prompt learning 还是会比其他的方法带来有一些明显的优势，特别是在一个小样本学习上，对吧？所以它的优势其实在只能说从 empirical 的角度去解释这么一个优势。那其实从可解释性的话，其实很难去解释说为什么这个prompt 学到了更好。那其实我觉得可解释性也是应该，这个其实是一个很大的一个研究问题嘛，所以很难去argue 说到底这个模型学到的东西是可解释的，因为可解释呃才会得到更好的效果，还是因为其他的什么方向的原因？对。
嗯。对然后那个小雨啊，这也是外语老师的那个学生，然后他有一个问题，但他那边在装修，我帮他问一下吧。就是就是您应该做了一系列工作，就是说把这种原图和结果图作为 prompt，然后去给这个大模型，然后它直接就能做，不管是做 prompt learning 还是做 inference learning，然后就直接能做，比如说分割啊、检测啊这些任务。然后他的问题是，其实我没太懂，看凯阳老师能不能懂，就是怎么判断。一个多模态的模型是否具有这种能力？是说，我理解是说，比如说这个它能不能做检测，是说我是不是要调它，我一定要调它，可能我调过它，它才能做这种任务，还是说就是任何一个多模态的模型，我只要 architecture 上本身有一个 design，它能做一些 unseen 的任务，但同时也是这种一个原图和结果图这种，我给它这种固定格式的 prompt，我是这么理解。
呃，他的问题是怎么去判断这些模型具
对，怎么去
有
判断？
啊？
对它怎么去？我理解
哦，
就是
刚刚消停一点了，刚刚消停一点，那个我来解
啊，
释一下吧，
我哪？
趁着他稍微对，是那个问题是，就是特别想问的一点是，有这么一个事情，就是大家知道说现在大模型它的能力是非常强的，然后很多时候我们就已经默认为说大模型什么task 它都能做，所以很多时候我们只是去说我们给它送入的一些。 那比如说给它送入一些句子，稍微做一些调整，它就可以去做很多 task。但是我想问一下，就是如何判断说 Vision Language Model 是否它本质上具有哪种能力？就比如说像刚刚凯阳老师有一页 PPT 是说把原图跟那个结果图就给它送进去，然后那个整个 Vision Language Model 就可以不，它整个 model 就可以去做那个 task 了。然后对对对，是这个。然后我想问，就是比如说就是第三个做那个第四个在做 segmentation 的时候，我如果只把这个车的那个左边的车灯给它抠出来，那个 mask 送进去，它是否也具有说可以把所有车的左边车灯给抠出来能力呢？
这一点确实很有趣。我们之前倒没有探索过，说如果只扣一个车灯的话，那这个模型会不会只会去识别左边的车灯？然后我的理解是，可能你抠车灯的话，它可能会把类似于车灯这种物体形状或者说材质的呃一些图片块都会抠出来。比如说对，一个是车灯，我都怀疑它可能镜子是不是也会抠出来。所以呃，对，所以这确实是一个比较有趣的一个可以去探索这种 in context learning 模型的这么一种一个特性吧。这可以去做一些实验，然后发现说它的一个识别能力到底是不是跟我们给的 in context example 是一致的。因为现在目前我们做的这些实验的话，其实它涉及到的这些任务都是呃比较一个怎么说，就是比较容易去判别出它的不同的，比如说像 edge detection，它的一些边缘化，那它这个原本的图片跟结果图边缘化这种很明显，但是你如果在细节的上去做一些特别是一个车灯啊或者一些车轮子的话，这个我觉得可以去探索一下它到底会出现出怎样的一个行为。这个很有趣的一个问题，对。
那与之相关的一个问题就是，您觉得那个大模型的能力的边界是我们如何去定义它的边界，或如何去探索它的边界这个事情呢？
嗯，如何去探索这个大的多模态模型的边界是吗？